Hello everyone! This is our second and last lecture for Chapter 14, an introduction to correlations and regression. In our last video, we introduced correlations and the Pearson-R coefficient. In this lecture video, we will discuss other types of correlation coefficients, chi-square, briefly, and linear regression. The Pearson correlation measures the direction and strength of a linear relationship between two continuous variables when x and y consist of numerical scores from an interval or ratio scale of measurement. Other correlations have been developed for nonlinear relationships and for other types of data. In this video, we will take a quick look at three additional correlations: the Spearman, point biserial, and the Phi coefficient. The beauty of these other correlations is that they use the same formula as the Pearson-R. They just have a different name due to the type of data being analyzed. The Spearman correlation, or RS, is used to measure the relationship between x and y when both variables are measured on ordinal scales. Remember from Chapter 1 that an ordinal scale typically involves ranking individuals rather than obtaining numerical scores. The Spearman correlation can be used as a valuable alternative to the Pearson correlation, even when the original raw scores are on an interval or ratio scale. Remember that Pearson-R measures the strength and direction of the linear relationship between two variables, how well the data points fit on a straight line. However, a researcher expects the data to show a consistent, one-directional relationship, but not necessarily a linear relationship. For example, for nearly any skill, increasing amounts of practice tend to be associated with improvements in performance. The more you practice, the better you get. However, it is not a straight line relationship. When you are first learning a new skill, practice produces large improvements in performance. After performing a skill for years, additional practice produces only minor changes. If you were to measure this with a Pearson-R correlation, you would find a correlation of 1 because the data do not fit. You would not find a correlation of 1 because the data do not fit perfectly on a straight line. So the Spearman correlation can be used to measure the consistency of the relationship regardless of its form. The point biserial correlation is used to measure the relationship between two variables in situations where one variable consists of numerical, continuous, interval, or scale scores, but the second variable has only two values. A variable with only two values is called a dichotomous variable. Some examples of dichotomous variables are male versus female, college grad versus not college grad, firstborn child versus later-born child, success versus failure, and so on. The Phi coefficient is used to measure the relationship between two variables in situations where both variables are dichotomous. An example of this would be if a researcher were interested in examining the relationship between birth order position and personality for individuals who have at least one sibling. Birth order position as firstborn child versus later-born child, and personality classified as introvert or extrovert. Although the Phi coefficient can be used to assess the relationship between two dichotomous variables, the more common statistical procedure is a chi-square statistic, which is discussed in Chapter 13. Chi-square statistic is more appropriate because it uses the proportions obtained from sample data to test hypotheses about the corresponding proportions in the population. Sometimes a researcher has questions about the proportions or relative frequencies for a distribution, especially when the data are nominal. So chi-square statistic is the appropriate procedure to use in these situations. Chi-square tests are non-parametric tests. In statistics, we have parametric tests, which are all of the statistical procedures you have learned in this class: z-test, t-tests, f-ratio, and correlations. The reason they are parametric is that they are all about parameters and they require that assumptions be met. There are times when experimental situations do not conform to the requirements of a parametric test. So in these situations, when assumptions are violated, we need alternatives to parametric tests. These alternatives are called non-parametric tests. There are non-parametric tests for every parametric test out there. So that was a very brief intro to chi-square and all you'll need to know for the final. So now let's get back to chapter 14 and talk about linear regression. Earlier, we introduced the Pearson correlation as a technique for describing and measuring the linear relationship between two variables. If there is a strong linear relationship, we can draw a line through the middle of the data points. This line serves several purposes. One, the line makes the relationship between the two variables easier to see. Two, the line identifies the center or central tendency of the relationship. And three, finally, and most importantly, the line can be used for prediction. The line establishes a precise one-to-one relationship between each x value and a corresponding y value. Now we will look at a procedure that identifies and defines the straight line that provides the best fit for any specific set of data. This straight line does not have to be drawn on a graph. It can be represented in a simple equation that most, if not all of you, will recognize. Our goal is to find the equation for the line that best describes the relationship for a set of x and y values. In general, the linear relationship between two variables x and y can be expressed by the equation y hat equal to a plus bx. Y hat is predicted y. This formula should look familiar. Remember, y hat equals mx plus b? In statistics, we use different placeholders for slope and y-intercept. So y hat equals a plus bx. In this general linear equation, the value of b is called the slope. The slope determines how much the variable changes when x is increased by 1 point. The value of a in this general linear equation is called the y-intercept because it determines the value of y when x is equal to 0. On a graph, the a value identifies the point where the line intercepts the y-axis. Because a straight line can be extremely useful for describing a relationship between two variables, we use a statistical technique that provides a standardized way to determine the best fitting straight line for any set of data. This statistical procedure is called regression, and the resulting straight line is called the regression line. The goal for regression is to find the best fitting straight line for a set of data. To do this, however, we first need to define precisely what we mean by best fit. For any particular set of data, it is possible to draw lots of different straight lines that all appear to pass through the center of the data points. Each of these lines can be defined by a linear equation. The problem is to find the specific line that provides the best fit to the actual data points. We define the best fitting line as the one that minimizes prediction error. Here is some background on how to minimize prediction error. To determine how well a line fits the data points, the first step is to define mathematically the distance between the line and each data point. For every x value in the data, the linear equation determines a y value on the line. This value is the predicted y or y hat. The distance between this predicted value and the actual y value is the error of prediction, y minus y hat. This distance measures the error between the line and the actual data. Because some of the distances are positive and some are negative, we have to square each distance to get a positive measure of error. To determine the total error between the line and the data, we add the squared errors for all the data points. This method is called the least squared error solution. The regression line is also known as the least squared regression line, or LSRL for short. Here is the graphical representation of what we just discussed. As you can see, the regression line y hat equal to a plus bx is the one that best fits these data because it minimizes the distances or errors between the line and the actual data points. And here's how we find the slope and the y-intercept to construct our regression line equation. To find the slope, b equals sum of products, SP, divided by sum of squares for x, SSX. Or b equal to r times standard deviation of y divided by standard deviation of x. To find the y-intercept, a is equal to sample mean of y, my, minus slope, b, times sample mean of x, mx. I will post a video that walks you through the calculations and interpretations of a Pearson-R correlation and regression equation.